Hey everybody, Thrasher here, coming to you from the left side of the screen this time. This video is still talking about systems, but it's actually an alternative way to approach problems. We already learned one method in D.8c, and we saw an example problem in part B of this kind of little mini-series. In C, I want to show you an alternative method. Now, this video is maybe a little weird because you actually never have to use this method if you don't want. Some people might find it a little easier, but as I'll explain in the end especially, this can certainly trip students up. So my go-to is the method discussed in the first two videos in this series, but this is an alternative way to go about it. All right, let's see what the heck I'm talking about. Here I have an example, kind of basic setup for one of maybe a variety of potential physics problems. I have a baseball and it's flying through the air. Maybe it's like a projectile motion problem. Maybe it's a problem where I'm analyzing the forces acting on this ball. But the key idea, regardless of the question, regardless of the physics scenario that this might be, we've always treated this baseball as a single object, right? It's always just been the ball, right? What's the velocity of the ball? What's the net force on the ball? What's the mass of the ball? But if you think about it, that's actually kind of a little weird, because a baseball is not just a single thing. If you zoomed in a little bit into a baseball, or let's say we cut a baseball in half and we looked inside, the baseball is made up of fibers and strands. And those fibers and strands, well, they're pulling on each other and they're tugging on one another. If we zoom in even more, they're made up of molecules, and they are exerting forces on each other. And of course, molecules are made up of atoms, and even atoms are made up of protons and neutrons. There are, in fact, all kinds of smaller objects that make up our baseball, and in fact, there's all kinds of other forces that are involved in our baseball. So, kind of what's going on? How come we've always treated this as one object? Is that wrong? Is that not appropriate? Well, no, it's okay that we treat our baseball as just one thing. Even though, depending on your perspective, whether you're zoomed in or zoomed out, how you are looking at an object, what makes an object, might depend on that perspective. Likewise, how we are looking at forces depends on that perspective. Okay, if we are looking at the baseball as one object, we have been ignoring all those forces inside, internal to the baseball. We've only been looking at the forces on the outside or external, like gravity, or maybe a baseball bat hitting the ball. Depending on our own perspective, we might be looking at certain forces, or we might be ignoring forces. We've been kind of doing this inherently without actually thinking about it, but now it's worthwhile to point out these differences. There are, in fact, many forces that are going on inside of a baseball, but up until now, we've only been looking at the outside ones. And that's okay. And the reason that's okay is because forces fall into two different categories. One type is known as internal forces. These are forces that are acting inside of an object, or, now that we've learned the word system, they're forces that are acting inside of a system. So, for example, even though there are innumerable number of forces, tuggings and pullings, something known as the electrostatic forces, heck, there's even something known as the strong force happening inside the atoms in a baseball, we ignore any of them. We don't focus our attention on these internal forces. Whereas there's also something known as external forces. External forces are those that are acting outside of the object or outside of our system. So in this example, maybe we would say this baseball bat would apply an external force. It's a force that's obviously not coming from the baseball itself or within the baseball. So these two different kind of categories, you don't have to memorize them. I certainly am not going to quiz you on a particular exam. Okay, the AP test isn't going to explicitly ask you for the difference. But these are actually important because Newton's second law is technically an application, or it's a discussion, it's a relationship of external forces. So what do I mean by that? And really, who cares? Why does this matter? Well, when we're looking at problems, we've been zooming in for the system problems. We've been spending time looking at one mass and what are the outside forces, like tension or like weight. But we actually could zoom out of our system. Even if our system is multiple objects, we could zoom out and kind of like treat it as if they were a single object. kind of like we've been treating a baseball as a single object. And in many ways it is, but to be honest, we can do that for anything. We can treat a system as one whole thing, so to speak, and we can look at the forces that are external to that system and apply Newton's second law to calculate things. And that can actually be helpful because sometimes zooming out, looking at a system as almost like a single object, it might be easier to calculate things. So that's a lot of weird kind of new jargon and these vague explanations. Let's see what I mean in practice, okay? The first thing I'm going to show you, while I'm not going to work this out, I've already done it if you notice, okay? This is actually a homework question that was in one of my own AP Physics classes. This was a problem where there were two masses of these two objects connected over a pulley with a string, and I asked to calculate the acceleration. And the first way we did this, kind of the normal way that we learned, was we zoom in and we focus on each object separately, and then we set up the sum of the forces for this object, we set up the sum of the forces for this object, we know their accelerations are equal, tensions are equal, and we plug in and solve. If you want, you can hit pause and you can really spend time looking through this, but suffice it to say, you can do it by zooming in on each object, and you could find out that the acceleration of our system was about 2.45 meters per second squared. I'm going to do this same subject, or the same problem, but by zooming out. And we'll see what that means by looking at the system as a whole. Okay, let's see what that means. So I still have my two different objects, but I'm going to zoom out. I'm in fact going to look at this whole thing at once. And what that means is when I try and set up Newton's sum of the forces, I'm not going to look at a particular object, I'm going to look at the whole system. And Newton's second law says that the sum of the forces is equal to mass, but if I'm focusing on the forces on the overall system, that's the mass of the overall system times the acceleration of the overall system. So what does that mean? Okay. If I look at my two objects here, now there are a couple of tension forces, right? There's a tension force acting up on this blue box. There's a tension force acting up on my orange box. But those are two forces acting between the objects. That's in fact akin to those forces that are acting within the baseball. Those tension forces are inside, internal to my system. So when I set up the sum of the forces looking at the whole system, I don't include them because they're inside. I only focus on forces that are acting outside of my two objects. And there are forces acting outside. What are they? It's the weight of these two objects. Weight is a force between objects and gravity. Gravity coming from the Earth, well, that's outside. If my system is these two balls or these two objects, gravity is still outside. So the weight forces on these two, the weight on this 3 kilogram mass, the weight on this 5 kilogram mass, those are external forces. So I'd still have to include them, okay? Now also, I still have like some of these forces like W3, they might cause the system to rotate in one way or to start moving one way, whereas the weight on my blue square would cause it to accelerate the other way. So I still have opposite kind of causations happening. Okay, one of these forces causes a different acceleration than another, so I should still consider direction. Let's say that the downward force, or this blue square moving downwards, is positive. Okay, so let's write out the forces of the system. Well, what is it? It's W3 and it's W5. Again, no tension because those are internal. They're inside. I'm only looking at external. I'm zoomed out. These external forces. So W3 and W5. W3, the weight force acting on this object, well, that's going to make the system rotate in this kind of way. If you look at my hands, it's going to make our object accelerate opposite the way the blue weight's going to be. So we should make one of them positive, one of them negative. Let's make this one negative because it's going to have an opposite effect to the weight of this 5 kilogram object and the weight that corresponds to it. That's going to equal, what's the mass of my system? It's the combination, 3 kilograms plus 5 kilograms. multiplied by the acceleration. Okay, so that's minus 3 kilograms times 9.8 plus 5 kilograms times 9.8 equals 3 plus 5, that's 8 kilograms, times the acceleration. So what's the acceleration equal to? I could just divide both sides by this. I have 3, and it's minus, negative 3 times 9.8 plus 5 times 9.8 divided by 8. And let's plug this into our calculator. Lo and behold, I get the same value as before in my prior slide, about 2.45 meters per second squared. Oh, by looking at the system as a whole, looking at the entire mass of the system, setting that as, or multiplying that by the acceleration of the system, and looking at the forces that are affecting the system from an outside, I can get the same values. And notice, I didn't need two separate free body diagrams. I didn't need to do the sum of the forces for my two objects separate. As long as I knew which forces were internal, which forces were external, and as long as I kept track of the fact that one of those external forces would kind of compete with the other, so they still should be subtracting with each other, I could kind of more quickly figure out the acceleration. So this approach can be easier sometimes for getting certain values, but there are some warnings, some things that you need to consider. This method can be faster. I think you'd agree that what I just set up in yellow, that's faster than what I had over here. Oh my gosh, that can be a lot of different steps. This method can, with a single equation, get you the result a little faster. But this can pretty easily trip students up. You really have to be aware of what it means to be looking at the system as a whole. You really have to consider what forces are internal and what forces are external. You also have to make sure you're understanding that you should be using the total mass, right? The system's mass is the total mass. You got to make sure you keep track of the total mass, all right? Now, when you're doing this approach, also you got to make sure that it's crystal clear that you're looking at the sum of the forces for the system. That should be very clear. If I don't see you indicating, if you're in my class in particular, if I don't see you indicating this, I'm just going to think you're using one of our kind of classic ways to analyze a problem. And then I might get confused and you risk me taking points off. So just like we should be showing our original equation, you should be showing something like this. That would be a clue to a College Board reader, to a professor, to myself, that, oh, okay, you're analyzing the whole system at once, and therefore it will allow the instructor or whoever is grading your problem to more carefully follow along. So this is just an alternative method. You never have to use this. To be honest, I like this method a little easier just because we do it so often. It's my go-to. But admittedly, as long as you're able to follow along and keep track of what is and what is not a force on the system, this can be an easier way to do some of these calculations. So the choice is yours. We'll see if you're in my class. The next homework will kind of utilize this method, okay? Because it is helpful in some problems. But like when it comes to these big math problems, you could use either type. But this is an alternative, okay? That's it for this video. Thanks for watching.